Alright, our next section and the subject also of our labs are going over the trapezoidal rule and Simpson's rule, which are basically better ways to approximate the area under the curve. We've talked a lot about trying to find the area underneath the curve using a Riemann sum where you have a curve and you break it up into a group of n intervals, and maybe you use like the left hand side and use the left hand side to construct rectangles and find the area of those rectangles. Is the Riemann sum, we used rectangles, but in a trapezoidal rule, instead of using rectangles, we're going to use trapezoids. We're going to do instead of looking at just going straight across the top of those, what we're going to do is we're going to go with a straight line across those top of those rectangles of each rectangle. So they're no longer rectangles, they're going to become trapezoids. We're going to connect the tops of those points with a straight line, and we should get a better approximation of what the area is. And the one thing to remember is that you're looking at a trapezoid sort of laid on its side, and the standard formula for the area of a trapezoid, draw a trapezoid here, is that the area is 1/2 base 1 plus base 2 times the height, and height being the vertical distance from one parallel side to the other. So the height would be the length of this altitude here. Base 1 is one side of your triangle, and base 2 is the other side of your triangle. And as you work through the lab, you'll see how this turns into the formula for the trapezoid rule, which basically says that we're going to approximate the area by doing, we're going to have delta x. We end up taking delta x over 2 and multiplying it by f of x0 plus 2 times f of x1 plus 2 times f of x2 plus 2 times f of x3 and so on, plus 2 times f of xn minus 1 plus just f of xn. So it's the first function value added in, the last function value added in, but then we double all the function values in between those two, and then multiply by delta x. So as an example, if I want to use the trapezoid rule to approximate the definite integral from 0 to 3 of x squared plus 1 using let's do 6 using n equals 6, so 6 subdivisions in there. So we need our delta x. Our delta x we're going to find like we did before. We're going to take the b minus a over n, so it's 3 minus 0 divided by 6. Back when we did Riemann sums, so 3 over 6. So that's going to be 1/2. And then I want to evaluate the function at every half a unit there between 0 and 3. So I want to find f of 0, f of 0.5, f of 1, f of 1.5, f of 2, f of 2.5, f of 3, and f of 3. So it should be 7 values. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7 different values there. I want to plug each one of those numbers into my function and see what the y value is. And by the magic of the internet, I'm going to make all those numbers appear. Ready? 3, 2, 1. And there they are. And so what we want to do the trapezoid rule is I'm going to take delta x over 2, so 1/2 divided by 2. It's going to be that my area is going to be approximately equal 1/2 divided by 2 multiplied by 1 plus 2 times 1.25 plus 2 times 2 plus 2 times 3.25 plus 2 times 5 plus 2 times 7.25 and then plus 10. So there's no 2 with the very first one and no 2 with the very last one, but 2 and all the others in between. And then if we crunch those numbers, we will get that the area is about 1/2 divided by 2 times 38.5, which would be actually 1/4 times 38.5, which gives us 27, whoops, that wasn't right, 38.5 divided by 4 is 9.625 as our trapezoidal approximation of the area underneath that curve, or that value of that definite integral. Of course, that one's pretty simple. We can do it just by hand to see what the actual area is. If I do the integral from 0 to 3 of x squared plus 1, I'm going to get x cubed over 3 plus x, evaluated at 0 and 3. So 27 over 3 plus 3 minus 0 over 3 plus 0 is going to give us 27 divided by 3 is 9. 9 plus 3 gives us 12. So our actual value is 12, but our approximation is 9.625. So a little bit better approximation, I think, than what we get by doing a Riemann sum, but there it is.